Okay, so hello everyone, and welcome to the third talk on our series of webinars from the aviation application section of Informs. This is our third one and the last one of this year. And today we have with us Arthur Dubois, Vice President of Engineering at Xwing. It's a company that was founded in 2016, and it aims to be a leader supplier on autonomy technology for aviation. And that's exactly the topic of today. So during today's talk, Arthur will discuss the key challenges in the developing and certifying autonomous flight technologies. And he's going to present an overview of key systems required and outline also the Xwing approach to solving these challenges. Arthur is an experienced airspace leader. Prior working at Xwing, Arthur also worked in several projects related mostly to eVTOL, to companies Joby and Kitty Hawk. So he's also a strong advocate for urban and regional air mobility, and he believes that aircraft autonomy and electrification will be fundamental in the next few years. In addition to this, Arthur also holds a master's in aerospace engineering from Stanford University and a bachelor's in mechanical engineering from McGill University. So, Arthur, I'd like to thank you again for your availability to give today a presentation. And I'm looking forward to learn more about the topic of autonomous aviation and this progress in the next few years and what are the prospects. So I hand over the floor to you now. Just before that, just mentioning to the audience that if you have any questions, please, you can write it in the Q&A or in the chat. And then in the end of this presentation, I will try to select some of these questions and ask to Arthur. Okay, so Arthur, over to you. Thank you.
Thank you for the intro. Thank you for inviting me. It's a pleasure to be here. Good morning again, everyone. My name is Arthur Dubois. I am the Vice President of Engineering at Xwing. So we're based in California, and we're developing autonomy technology for aircraft. And so today I want to give folks here a flavor of that technology. I think it's going to be obviously difficult to go very deep in the weeds, but I've picked a few examples and a few highlights that I wanted to share about the technology. So my goal is to kind of give you a quick company overview. I want to spend a little bit of time also talking about the applications of the technology. And then two things I want to do after that. One is kind of lift the hood on what it takes to build an autonomous aircraft in terms of systems and key technologies. And then I want to spend a bit of time talking about how we approach this new paradigm in aviation, where we've effectively, moved the pilot from the aircraft to the ground, and that triggers a whole set of questions on the safety side and how we show that we are meeting the existing safety targets. So without further ado, I'm going to jump in. So we were founded in 2016. The objective of the company was always to develop autonomy technology for larger aircraft. So we're not doing drones, we are doing larger aircraft. Now, the first few years were really focused on proving out the technology at the concept level and using smaller platforms to do that. But in 2019, the company acquired its first Cessna Caravan. So Cessna Caravan is a well-used aircraft across small cargo applications and also passenger applications. There's thousands of them flying in the world today. And so that is our first platform on which we are implementing autonomy. We also in 2020 acquired an airline that flies Cessna Caravans because we wanted to learn about the operational side of the business. And that actually has been a very important decision in our history, because I don't think you could certify autonomy without really understanding operations. From there on, in 2021, the technology came together for the first time on full-scale aircraft at a prototype level. And so we did a full autonomous gate-to-gate flight, and the video is on YouTube if you're interested. And from there on, the technology has really matured from prototype to being a technology that is now undergoing a formal certification project with the FAA in the US. As far as I know, we are the only company that has a certification project for an uncrewed large-scale aircraft. And so we'll be continuing to work on that in the next few years to bring this first sort of system to market. Quick glance at the leadership team. So our CEO is Fred Cromer. He's the former president at Bombardier Aerospace. And then our CTO, Max Gariel, is a former chief engineer at Collins Aerospace. And then last but not least, Earl Lawrence is our chief compliance and quality officer, and he was previously the executive director of aircraft certification at the FAA. So you can see we have a pretty experienced leadership in aviation. I'm going to spend a few minutes here playing a video for folks here. I think the video is going to do a better job than I can at explaining the fundamentals of the system and how the technology we're building works. Let's just hope it plays. There we go.
Introducing Superpilot, Xwing's autonomous flight system. Xwing's Superpilot system addresses every aspect of the pilot's role. From a mission control center, a remote operator continuously monitors the plane, providing operational control, coordination, and communication. Our uncrewed aircraft seamlessly integrates into the national airspace system. Let's take a closer look at how Superpilot works from gate to gate. Before a flight, the remote operator validates an auto-generated, path-optimized flight plan and submits it to air traffic control for approval. When deployed in commercial cargo service, the same procedures required for a typical crewed Part 135 cargo aircraft are followed and supplemented with additional steps needed to support unique aspects of an uncrewed mission. Prior to flight, the ground crew inspects the aircraft, initiates the Superpilot system, and loads the cargo.
Automated pre-flight checks initiated.
Superpilot conducts an automated pre-flight inspection to ensure all systems are functioning properly. The remote operator reviews the weather and obtains clearances from air traffic control. After loading, Superpilot validates weight and balance data. The ground crew secures the aircraft and clears its surroundings. Then the remote operator initiates an autonomous engine start. Once air traffic control provides a taxi route, the remote operator confirms all systems are go and initiates the auto taxi sequence. The aircraft automatically stops at key points along the taxi route, and the remote operator coordinates with ATC before proceeding to the next taxi phase. Using onboard sensor data, detection algorithms run constantly to allow Superpilot to avoid any potential obstacles. While taxiing, the remote operator listens to ATC instructions and may alter the route as instructed. When cleared by ATC, the remote operator authorizes Superpilot to enter the runway for takeoff.
Auto takeoff initiated.
Superpilot, under the supervision of the remote operator, monitors system health and performance and its surroundings to ensure a safe departure. Superpilot then executes a takeoff and climb out automatically. While in the air, Superpilot maintains an optimal flight path based on the uplinked mission plan. Superpilot continuously monitors onboard system health and, if needed, can automatically conduct all the emergency procedures that a human pilot would normally follow. For example, Superpilot continuously monitors and evaluates the glide path from its location to the most optimal landing site from all suitable options. In the case of an emergency, Superpilot will initiate a reroute to this landing site. The remote operator may redirect the aircraft to a different landing site if desired and may communicate with ATC as needed. The Superpilot system also includes an advanced detect and avoid system. By fusing data from multiple sensors, the detect and avoid system monitors other airborne traffic in order to maintain a safe separation. Superpilot has sensors that can see in the dark, in weather, and in sun glare, thereby enhancing flight safety.
Traffic conflict anticipated.
Superpilot is also capable of autonomously executing an avoidance maneuver. Superpilot is able to detect any potential hazards with plenty of time for the remote operator to coordinate an appropriate response with ATC. When the plane begins its destination arrival sequence, Superpilot performs a number of self-checks before landing to ensure that all systems are operational. The remote operator communicates with ATC and receives instructions. Approach procedure updates may be transmitted by the remote operator to modify Superpilot's auto-land sequence. Superpilot maintains the runway centerline using conventional ground and space-based aviation navigational aids. As the aircraft approaches the runway, Superpilot engages onboard visual navigation sensors to identify the runway and continuously evaluate its ability to complete a successful landing. Until completion of the landing, Superpilot uses onboard sensors to continuously verify that the runway is free of other aircraft and obstacles and guides the aircraft to touchdown. Just like at takeoff, Superpilot executes the landing and any emergency procedures on its own. After taxiing to its apron, Superpilot shuts the engine down and the ground crew offloads the cargo.
Good. Okay, so hopefully that gives people a good overview of what the system does and how it works. I think the general premises of it at a high level is that we're taking the onboard pilot and we're moving them to the ground, and they're becoming a remote operator as shown here. The other consequence is that the pilot the remote operator no longer has the ability to actually directly fly the aircraft. They are able to set the direction for the flights and give kind of high-level commands to the aircraft, but the workload on the pilot is greatly reduced. And because of that, we are, it's very believable to think that one remote operator can now oversee multiple aircraft. The other piece is that in the case where the remote operator is incapacitated for whatever reason, or in the case where the communications link between the aircraft and the ground, is inoperative for a while, the aircraft is fully capable of getting itself onto the ground. But you can imagine now a world in which, you have a centralized mission control center where a group of remote pilots oversee a group of autonomous aircraft. And they don't all have to be the same type of aircraft. They could be, the same person could oversee a Caravan, an eVTOL aircraft, or another type of vehicle even. And so what we're really thinking about our technology as the kind of foundation of a different kind of transportation system that we'll be using in the future. Talking a bit about applications, I'm going to spend a tiny bit of time on this. I think at a high level, the key piece that our technology offers is kind of a few advantages. So one is pilot shortage. There's, you guys might know that there's a big problem with pilot shortage in the US, and that's not going to get any better as aviation scales with these new urban air mobility vehicles. So these cargo operations of the type that we're flying, they're the least interesting type of flying for pilots. So if you're flying a 787 with a major airline, that's a really cool job. But if you're flying cargo from a small airport to small airports, there's not a lot of pilots who want these jobs. And so there's an even more acute pilot shortage problem there. The other piece is safety and security. I think a lot of small aircraft accidents come due to pilot errors, and we feel like a system is going to be able to improve on that. Lower operational costs, we'll talk about that in a minute, but effectively you are spreading the pilot across more aircraft, and so the cost is diluted, and the pilot cost in the whole equation really comes down. And then optimization for peak performance, while you're no longer carrying the human, the weight of the human, so you can only carry cargo and really maximize the use of your payload. Going forward, I think, we're working right now on certifying our technology on a Cessna Caravan. And the clear application is working with cargo operators. So, we have an airline that's got about 35 aircraft. FedEx has a much larger one. We work with UPS. There's a lot of these small airlines out in the country flying Caravans, and so that's the first application for us. There are military applications also mostly in the cargo space. And then there is the advanced air mobility field, which is this sort of up-and-coming new application that we'll talk about just a little bit here. The same technology applies across all these different types of operations, all these different types of platforms with very little changes, it turns out. Going one level deeper, so our sort of thesis is that there's this sort of inevitable transition of cargo, both across commercial and defense, towards autonomy, where there's few reasons why in 10 years or so, the majority of cargo aircraft wouldn't be autonomous, specifically the small aircraft. And then, the beyond that, that in itself is already multiple hundreds of billions of dollars. And then beyond that, there is a even bigger potential for air taxis and air mobility in general, which is sort of this unknown at this point. And so we're thinking about it, but there's still certainly a lot of questions around what that's going to turn out. I'll talk briefly on the cargo piece. So I think the way that small aircraft cargo works today, just to give you a sense, is you have a pilot, and they're going to take off in the morning at 7 or whatever. They're going to fly 1 hour. Then they're going to have to wait all day on the clock for cargo to be loaded back into the aircraft. So you have to pay them for a full day of work for really effectively what is something like 2 hours of flight a day. So it's pretty inefficient from the usage of the pilots. And so the premise of autonomy is now the pilot sits in a room, they can pick up a flight from 7 to 8, another one from 8 to 9, 9 to 10, and basically fill their day with actually flying time. And therefore you can dramatically increase the use of the pilot, and that makes your ability to generate margin much higher in a space where margin is really, really tight to begin with. So that's the cargo commercialization potential. And then beyond that, on the advanced air mobility side, there's folks talking about this $1 trillion opportunity. In the way that I've always thought about this is, I think the opportunity is actually medium until you get autonomy. And I think the only way to get to the $1 trillion market is with autonomy. The reason is fairly simple in that, if you have a 4-seater vehicle that has a pilot, first off, you have to pay the pilot. The vehicle costs more because it's a bigger vehicle. And the odds that you're going to fill the 4 seats each time are actually pretty low in advanced network. And so what it also works out to is that you end up with a price point of $4 to $6 per seat mile. And that makes it really difficult to generate revenue because that's 3 to 4 times the cost of an Uber. So you're not going to scale to a $1 trillion market if you charge 3 or 4 times the cost of an Uber, because people simply won't be able to afford it. The counterpoint to that is if you have autonomy, then you can build a smaller vehicle that's 1 seat that is cheaper because it's smaller, and you always fill it because it's only just 1 seat in there, so it's always on demand. And so once you work all that into a unit economics model, you can get down to the $1 to $2 per seat mile, which is the cost of an Uber. That's actually an affordable solution. And so to me, that's the key unlock to getting to the scale in urban air mobility. And until we have certified autonomy, we're just not going to get to these larger opportunities. All right, so let's talk a bit about the technology and kind of what's under the hood. So the way that our system works is that it's very aircraft agnostic in that the technology stack can be, to a large extent, applied to any aircraft, and it can make it autonomous during all stages of flight. So that includes the normal flights, so taxi, takeoff, cruise, and so on, but also emergencies, like if you have a fire in the cabin, if you have a loss of engine, if there's ice on the wing, the system is capable of dealing with these types of contingencies. And then we'll talk about it a little more, but there's kind of a variety of key systems that are sort of new compared to what's done currently in aviation. So you have hazard avoidance systems, you have a detect and avoid system, systems that deal with emergency landing, systems that deal with vision, using cameras to figure out the position of the aircraft and get it to the ground. And so these systems have sort of matured over several years since 2021. And what we've done in our certification program is basically take the maturation of that system and re-architected it into a certifiable solution. And this is what we're currently certifying with the FAA today. To give you kind of a sense for what are the key pieces here, I'm not going to spend a ton of time necessarily here, but I wanted to give folks just kind of situational awareness. So the kind of subsystem, the core components of the autonomy, the Xwing autonomy stack are basically kind of these boxes here. So you have at the center, you have your mission management system. That's the brain of the vehicle. It's basically getting inputs from all the other system, and it's making decisions about what to do, and it's generating flight plans if it has to. So it could be, it knows there is an aircraft coming our way, and it has to avoid that aircraft, and so it's going to generate an alternate flight plan autonomously. So again, central brain here in purple. To the right of that, we have the autoflight system. That's actually the system flying, moving the controls and all that, and actually doing the all the low-level flight, basically. Underneath, vehicle management system. So that system deals with keeping the lights on, looking at the health of the vehicle. Is there something wrong with the engine? Is there a fire on board? And so on and so forth. And so it's constantly communicating with its boss, the mission management system, to let it know if something is going wrong with the vehicle. Yellow is the hazard avoidance system. So that piece is about looking around the aircraft and trying to detect anything that's coming our way so that we can make appropriate decisions. And then the last onboard system is the communication management system, which deals with receiving data from the ground. And then on top of that, we have a set of off-board systems, which are the ground control station with the remote operator, and then the communication system, which sends data from the ground into the aircraft. So what I'm going to do from here is just kind of give you guys a few bits and pieces of highlights on each of these systems, or some of these systems, let's put it that way. Okay, so this is an example of the mission management system, and so I'm gonna play this video. What you're seeing here is basically the cameras on board the aircraft fused into one augmented view. And at the bottom, you have the compass right here. And so what you're seeing is basically the blue route is our nominal route. And what you're seeing in yellow is a calculation that the mission management system is constantly carrying out. So as we're progressing, it's always thinking about, what if I lost the engine? How would I proceed? And so this calculation is effectively looking at how would I get to an airport knowing that I've lost my engine. And as we progress in the flight, you're going to see this yellow line evolving. And I'm going to skip forward. So right here, you see it's actually chosen a different path because it has to shed energy to get to the ground. And so it's optimizing for how to get to the ground safely, knowing the position of nearby airports. And so right here, it's looking at landing on this runway that we see. And then it's going to, in a second, what it's going to do is going to decide that there's actually a better runway to land at, and it's going to update the path according to, its calculation. So shortly. All right, there we go. So right here, it's actually switched path from one runway to another, and it's constantly basically carrying out that optimization calculation. Okay, so it's constantly optimizing for trying to get to the next airport. That's just one example of this, but it's doing that for engine failures, it's doing that for icing, it's doing that for all sorts of contingencies in parallel. And from there, you can tell that a human would never be capable of doing that, but this is where computer systems are truly helpful in bringing the next level of safety, and is constantly being on the lookout for anything that might go wrong with a plan on how to address it. And this is just a little bit the details of how it works, but it's really about looking at winds, looking at the characteristics of the aircraft, and how to properly get to the ground safely. Another example is detect and avoid. So basically, this is a system that looks around us and looks at an aircraft coming our way. And so I'm going to play one of the videos here. So what's going on here is that we have an aircraft coming at us. So you can see the N-84 VC. That's what you see in the background there on the camera. And so the system is automatically flagging that for us. And down here in the compass, what you're going to see in a second is this yellow arrow that's going to enter the field of view. And you're seeing these kind of circles there, these ellipses. And so what this is actually showing is if we were to continue forward, this is when we're going to get pretty close to that other aircraft. And so what the system is going to do is, as we enter the kind of orange ellipse here, it's going to go and initiate an avoidance maneuver for us, because that system has automatically detected that there was a danger. And so, it's doing that across the board, and it's able to kind of detect obstacles and automatically avoid them in case the human hasn't done anything. So right here, we've initiated an avoidance maneuver to avoid this other traffic, and then we are going to an alternate path. I should clarify that all of this is actual flight test. This is not like synthetic data. This is actual stuff that we test day in, day out at our facility. I'll move on here to the next one, if it will let me. Come on, there we go. So another piece of the system is visual navigation. So the way this works is when you come into land, you always have a GPS, and GPSs are pretty good, but in order to truly get safely into the ground, you need an additional type of navigation system. And so the way we do this is we have cameras on the aircraft, and the cameras will have the runway in the field of view, and then we have a machine learning algorithm that detects the runway position and back calculates the position of the aircraft with respect to the runway using the image. And so in practice, the way we work, and I'll show you the video here, is we have these two systems. We have the GPS on one side and the camera-based localization on the other. And they run in parallel, and they cross-check each other, and they augment each other. And what this is showing here is on the top, you're going to see the actual runway with the corner points that have been identified by the machine learning algorithm. At the bottom, you are going to see the calculated position based on GPS in purple and the calculated position based on just the camera in blue. What's interesting is as you're far from the runway, you're going to see the blue airplane jump a lot. And as we get closer and closer, you're going to see the blue airplane get a lot steadier. And actually, as you get above the runway, the accuracy of the camera-based solution becomes higher than the accuracy of the GPS. So these two solutions kind of complement each other at various stages of the approach to kind of get you to a really high level of accuracy at any point. And so again, you see the blue jumping around, and as we get closer, it's going to become much, much, much steadier. All right, I'll talk briefly about a couple more applications, and then I want to talk a bit about the safety case here. So the ground hazard avoidance system is using LiDARs that are mounted under the wing of the aircraft, and it's not using any sort of machine learning, but what it's really doing is kind of receiving data from the LiDAR and using our algorithm, segmenting the ground out, clustering objects, and tracking their state to make sure they're not going to collide with the vehicle. And so that system is key for us to navigate, but we only really use it on the ground. All right. And then I think the last piece of the system that I wanted to mention is the pre-takeoff and pre-landing runway checks. For people who follow kind of aviation incidents, there's been a number of cases of near miss on runways recently. And so a system like this can be used for both autonomous aircraft, but also real aircraft. Oh, sorry, not real aircraft, but piloted aircraft. What you can do is coming into the runway, there's a camera that's looking at the runway and detecting, vehicles, people, aircraft, and so on and so forth. And so, that piece is key to make sure that we never come in and land on top of another aircraft, as you can imagine. Okay, so last kind of topic I wanted to cover today is I want to talk a bit about aviation and safety and what it means to introduce something as new as autonomy in this existing aviation safety paradigm. So one of the things I like to do sometimes is just think about how incredibly safe and advanced aviation is today compared to the early days. I think, everybody here has flown on a commercial aircraft probably, and you don't even think twice about it. And I think that's just incredible. And we should pause to think about that, because you're flying in this basically thin can. It's a pressurized can with millimeter thin walls. You're flying at 500 miles an hour, and there's this massive turbine right next to you that's spinning at 10 to thousands of RPM. And there's this just super high temperature controlled explosion that's happening at the center of it. And it never fails. I mean, literally, it only fails once in a billion flight hours. This is just incredible, right? Now let's think about how we got there. I mean, first off, I think that if these airplanes didn't exist today and you try to design them from scratch, people would think you're crazy because it just sounds so incredibly complex. But it is safe and it works. And you know, just looking back, right, like the way it got to that level of safety is basically through a giant trial and error experiment. What was happening in the early days is we were simply tolerating higher, sort of lower levels of safety, which I'm not saying we should do this today by any means, but it's worth thinking about, you know, the fact that this is how the regulations came about. You know, over time, there was this sort of organic growth of engineering or regulations to kind of converge to the safety paradigm that we have today. But it took many accidents, many errors, incidents to kind of progress towards where we are today. Now, if we want to introduce something transformational like autonomy here, you know, we're going to think about how do we bring in that new technology without having to repeat all the accidents that have happened in the past. And so we have to replace the trial and error piece with formal engineering, which is a little bit what I want to talk about today. So looking back, let's just look at an accident, right? So what is it going to take for two aircraft to collide in the, you know, in air? So, you know, to kind of simplify it, let's just say that four things happen, right? So first off, if these two aircraft run into one another, there's a system that didn't do its job. They probably should have been detected sooner. So something went wrong on the system side. There's probably something wrong on the operations side because these aircraft shouldn't even be on the collision course to begin with. So that's another thing that went wrong. The pilots on board didn't see each other, so both pilots hadn't noticed each other, and so there was something wrong with the pilot. Something happened. There was an issue, a failure probably on their end. And then, you know, just bad luck. I mean, aircraft are pretty small in the grand scheme of things, and so, you know, the odds of them just actually physically running into one another actually aren't that big. So, you know, if we think about the protection layers that have failed for there to be a mid-air collision, right? There's an aircraft system layer that's failed. There's an operational procedures layer that's failed. There's a pilot that's failed, and then there's just the luck factor that's failed us. And so the way that a lot of aviation people think about that is kind of what they call the Swiss cheese model. So the way to think about this is there's kind of various layers of protection, various barriers to incidents. And you know, one of them is what's on the aircraft. The other one is the operational procedures, the training of the pilot, and you know, just the fact that the sky is pretty empty in the grand scheme of things. So for there to be an accident, there needs to be a gap in each of these slices of cheese in the exact wrong way, such that there's actually a collision. So that was just kind of an example to introduce this concept of the Swiss cheese model. And you know, now we're talking about autonomy. So we're going to talk a bit about what is it like to actually remove the layer that's the trained pilot, and what does it do to the other layers once we do that. So, you know, just at a broad level, aircraft safety sort of hinges on kind of this organic patchwork of operational regulations. So that's the procedures here, aircraft regulations, and then the training and the awareness of the pilot. And you know, like we said, this is not like this has been like well thought out from the get-go. It just sort of converged to that. But there hasn't been like this formal analysis to get to what are the regulations in each of these areas that lead to safe enough operations. So now we're talking about this new paradigm where we've effectively reduced the role of the pilot. It's now a remote pilot. We've increased the role of the aircraft. It's now an autonomous aircraft. And we need new procedures to operate the whole thing. So, you know, we're going to need to go and think about re-architecting the aircraft and you know, the regulations for the aircraft, the requirements for the aircraft, the requirements for the procedure to cover for the removal of the pilots. So let's talk about an example here that's hopefully going to put this in context for folks. There's a regulation that's a part of an operational regulation, 91-113. And what it basically says is that the people flying an aircraft should maintain vigilance. to look for other aircraft that may be coming their way. And, that's a very qualitative term. I mean, vigilance is not something you can really quantify. But empirically, there was, if you had a licensed pilot on board an aircraft, that was kind of sufficient to meet the intent of that 91.113 rule. Now, you can see that that's not really designed for systems. How, if you want to put a system in there that's performing that same task, like how good does it have to be? Like how good is maintaining vigilance? So how good do you have to be at detecting these aircraft around you? And you could think about this of like, well, I have to be just as good as a human, so I might need to go and quantify how good humans are at this. It turns out that it's actually incredibly difficult to do it that way. And so you don't even really want to approach the problem that way. And the way that Xwing is thinking about it is really, okay, let's think about operationally. How good do we have to be, right? Like, so what is the acceptable rate of collision during operations today? And this is just looking at empirical data. How often do planes run into one another? It's very rare. But at least it gives us a number to start with. But from that kind of operational number, we can say that at the operational level, this is the type of performance we would like to reach. Now, the question is, like we said before, the overall operational performance is a combination of all these various slices of cheese. And so, and now we no longer have the pilot. So we got to think about, in order to get to that overall rate of accident, what percentage of that do we assign to aircraft system? What percentage do we assign to operational procedures, and so on and so forth? And so the way that we have approached it is let's think about a series of analysis. So we have on one end, we're performing analysis on the system side. On the other hand, we're performing analysis on the operational side. And we're going back and forth between the two, right? We're saying, well, maybe the aircraft covers so much of the requirement, and maybe the operational procedures and the mitigations in place there will cover so much. And then we go back and forth between the two until we find an equilibrium that, the system can meet, that's going to overall get us to a level of safety that is acceptable at the operational level. So there's kind of this back and forth analysis between the two that leads to kind of two sets of requirements, an aircraft system requirements and then a set of operational requirements. And that is how we go about kind of defining how good a system has to be in this new construct where the pilot is no longer as big a part of the safety case as it used to be. Okay, so I think I'll stop here. Hopefully, that sparked some interesting thoughts and questions with people. And then from there, I'll take a few questions.
Thank you very much, Arthur. It was a very interesting presentation, and you finish on time, so I still have some time to have some questions. In the meantime, I ask the audience to start using Q&A, and you can type some of your questions. We already have one here, or two actually, from the same person. So Maureen Namukaza, and they are both very interesting questions. So the first one, so first he says, thanks for the great presentation, and he would like you to explain the following points. And the first one is, does Xwing have a plan to scale multi-vehicle operations or even have a ConOps for multi-vehicle operations? That's the first question.
Yeah, the answer is yes. It's not something that we've necessarily shared publicly, but there's no questions that our plan is to look across multiple platforms, and we've already started work in that direction with a variety of partners.
And the second question is, beyond initiating an autonomous flight with a super pilot, what other roles does the remote operator have? Do they just monitor the flight path and wait? And if that is the case, how do you plan to keep remote operators or the remote pilots engaged in such tasks? Because they might more easily getting a bit bored, right?
Yeah, I think so. First, that's a great question. There's been a nuance in this. So there is what they can do and what they have to do. So really, the pilot is what we call, the remote pilot is what we call over the loop. And so what they do is that they're allowed to intervene. So what they can do is like change the destination airport. They could change their flight plan. They could ask the aircraft to land immediately for whatever reason. They also communicate with air traffic control. And so if there's instructions from air traffic control, they might relay that to the aircraft. So they have some amount of workload. I think it's a good question in the sense that there's some real human factors analysis that's going on to make sure that the pilot stays engaged. I mean, this is getting really into the weeds, but I guess I'll leave it as we're doing quite a bit of human factors analysis to make sure that the workload is appropriate and that we keep the pilots engaged during the flights. And I think specifically at first, when we only have probably one aircraft per pilot, we have to be particularly careful about this. I believe that the workload is going to increase once we're able to do multi-aircraft per pilot.
Yeah, I agree. I mean, if you start having a pilot coordinating many aircrafts, then they will engage in many different aircrafts. By the way, do you have an idea of how many aircrafts do you think a remote pilot would be able to take?
So I think the answer actually depends on what phase of flight. I think for takeoff and landing, right, you might want to remain one-to-one for a while. But as you're talking about, cruising, I think typically what would happen is you could see something like 5 to 10 aircraft for a given pilot, with the understanding that if something goes wrong, it's kind of like a dispatcher like ATC works today. When an air traffic controller manages aircraft and something goes wrong with one of the aircraft, they're going to pass on all the other ones to somebody else so that they can focus on the one that's not doing well. So we expect kind of a similar system for Xwing there.
All right, let me just go to another question made by Ray Mattison, and he's asking, what is Xwing's business model? Is your intention to provide B2B avionics similar to Garmin?
So I think early on, right, so we have our own airline, and so I think our first customer is ourselves, and that was key to kind of get us into operations, right? So I think there is there's an aspect of being our own customer at first. Beyond that, I think the key is yes, it's to provide a service and a set of equipment to other aviation players to enable autonomy for them effectively.
Thank you very much. Another question. So do you expect to begin operations in the US first, or are there other regulators more receptive to your technologies? I believe you are more inserted now in the US to start, or have you started already something else with other regions?
Yeah. The US is kind of what we're looking at. I mean, that's the work that we've done to date, and I think the FAA has been extremely open to working with us. So far we're spending most of our time in the US. We are thinking about other markets, but I think our focus really is trying to get the FAA certification, because that in itself is a thing that a lot of other regulators around the world will see as a key, kind of the key milestone. So I think just getting a type certificate in the US actually opens up a lot of opportunities abroad as well.
All right, thank you. So one question I have that's more related to the work that I develop, which is more in optimization and operations research and so on, is what kind of, if you see that operations research, and in particular optimization, informs is about operations research, could somehow contribute to autonomous vehicles, and in which way could also contribute to Xwing success?
Yeah, so I think there's a lot of work that can be done in optimizing decision making. So when we're talking about path planning and decision making, there is such a thing as an optimal decision. And so I will say our approach to the problem right now is purposely simpler, just because we want to get to a point where we're able to really explain clearly what the vehicle is doing. But I think beyond that, there's a lot of interest in trying to get to the next level of decision-making capabilities and path planning capabilities. And that requires a lot of, I will say, explainable optimization. So it's one thing to get the optimal answer, but the other key is being able to demonstrate why it's the optimal answer and why it's not going to do sort of anything stupid, if you will, on the safety side.
Yeah. By the way, do you envision that with this autonomous aviation will be able to increase throughput of capacity throughput at airports, because everything is automated, so it's much more controlled, the separation between the aircrafts. Do you envision that also? And that relates also with optimization of the operations. So if everything becomes autonomous, there might be the possibility of optimizing coordination between flights. So I believe that is a very long vision at this stage.
I think you're right. It's a long-term vision, because I'm not seeing big passenger aircraft become autonomous anytime soon. And I don't think they necessarily need to be. I mean, again, it comes down to, like, you have one pilot, and if it's one pilot for 300 passengers, the cost of the pilot isn't as big a factor. So you won't see a need for full autonomy on bigger airliners sooner. So you'll still have to contend with a lot of pilots in the space. But I think down the line, yes, that's true. And the other place where that's true is if you look at, higher density urban air mobility operations, then you have a massive amount of optimization on the network side, and that is a problem that a lot of these UAM players are looking pretty deeply into.
Yeah, I agree. Li Shuai, you raise your hand, so I'm not sure if you want to make a question.
Yes,
In the
I wanted
meantime,
to
we have
ask.
two more questions here, so but you can go ahead first.
Thank you, Nuno. I got the chance. So, Arthur, thank you very much for the presentation. I learned a lot. Question related to optimization, but more focusing on the fuel efficiency and environmental side. So, I could imagine that by enabling the autonomous flight, we could do better than human pilot in terms of the optimized flight profile, speed, altitude, etc. I don't know if at Xwing you have done this kind of comparison and how big the difference is.
I will say we haven't done it ourselves, but it's certainly something that we are interested in. The numbers we have at this point are something like 5 to 10%, if we do our job really well. So that's one factor. I think the other factor, right, is simply that you're not carrying a human on board, and so on a per kilogram of payload, you're doing a better job at carrying things. But you're right. Beyond that, there's quite a bit of optimization, because the system flies, I mean, to a few feet, right? It's incredibly precise and smart in the way it flies the aircraft.
Great, thank you, Arthur. Yeah.
Thanks, Li Shuai, for the question. We have another question. Few more questions online. Shiji Kong is asking for the comparison between current eVTOL and the scalable single-seat UAM.
Yeah.
Seems that the later one requires much more remote pilots. From this perspective, is it a better solution?
I will say yes, but let me try to answer the best way I can. So first off, you're right. If you assume that it's one remote pilot for one aircraft, then yes, it's less interesting. I mean, even that is more interesting, because you are only carrying the passenger, right? So the minute you do that, you're only really paying for the weight of the paying passenger on the vehicle. You don't have to pay extra money to carry a 200-pound or so pilot. So just that in itself is an improvement. But you're right that, like, if we stay on the one-to-one paradigm, the scalable one-seat UAM solution is not going to get to the price points that we want. So there's a requirement to get to a 1-to-5 or a 1-to-10 to kind of dilute the cost of the pilot across a variety of flights. The other advantages of keeping your pilot on the ground is that they're not waiting between flight. They can immediately finish a flight and pick up the next one. So there's an efficiency piece of how you operate your network that remote pilots also get you, that you wouldn't get from piloted operations.
I think very good answer. The next question is again from Ray Mattison, and is asking, is autonomous flight expected to be visual flight rules or instrumental flight rules? That goes a bit related to what I was mentioning before. So are we able to reduce and minimize separation requirements by being able to have this more autonomous approach?
Actually, we're not, I mean, for entry into service, we're not looking at VFR flight. We're looking into IFR because it's much more codified, and there's separation services provided in some areas by air traffic control. So it's actually, for us, it's much easier to do IFR. I mean, our system flies on instrument. Our system doesn't fly on vision for the most part. So VFR is actually an expansion we'll probably do in the future.
Yeah, makes sense. Also because you want to be at the safe mode at this stage. You don't want to already take the risk to reduce the separation between aircrafts. Another question from Vincent Grenon. What type of communication system are you using between the aircraft and the ground station in order to obtain the data from the aircraft?
Yeah, so it's typically a patchwork solution, and the reason is that, you know, not every system works perfectly everywhere, and the other reason is that there's various levels of criticality for each type of data. So at a high level, we're using, you know, satellite communication. We're using line of sight radios. So these two things are used for more critical data, and then for data that's non-critical to the flight, we're using actual LTE networks, so for cell phone networks. The type of data link changes dynamically during the flight based on the availability of a given data link, and then the criticality of the information and the cost of sending data from the aircraft to the ground and vice versa.
Last question. I don't have any more questions here, but we still have 1 minute, and then we can conclude this webinar. Just asking you, what are the next steps? What do you think is going to happen in the next few years?
Well, so I think the first piece is you know, finishing or being very focused on getting to a certified aircraft. So that's one thing, and then starting integration on additional platforms. Which you know, we've started work on to some degree already.
There is another question that just appeared now, so we still have a few seconds. So for those of us considering this technology, how would our project managers reach out to Xwing, and what level of maturation is of interest? And what types of aircraft is Xwing interested in working with?
You guys have my info, so you can always forward me, you know, emails and requests. I'm happy to field those. Level of maturation, I think it really depends on the area. There's like if we're talking about more advanced, let's say, perception technology, or even some of the path planning stuff, we are starting to think about next generation. I will say that's not our priority right now. So our priority is getting to the certified solution. So we are looking at future stuff in these areas. But in general, I will say for kind of implementation in the shorter term, it's really the certifiable technology with some amount of pedigree or some path to have pedigree in aviation. What types of aircraft? I mean, we typically target smaller aircraft, but we also have talked to players that have bigger cargo or airplanes out there. I will say that our focus right now is more on the smaller platform. So it's like, think of in the US what would be a Part 23 aircraft, or even small helicopters and things like that.
Arthur, thank you very much for the presentation and also for answering all these questions. I think the audience was interested because you had a good amount of questions. And that's all for today's webinar. We will have more next year, so Happy New Year for all of you. And probably next webinar is going to happen in January or February. But we will be publishing it online. There is also a question if we are going to make this presentation available. We will be making the presentation available online in the aviation application section Informs website. So thank you very much, and hope to see you again soon in our next talk. Thank you.
Thank you.